In this video, we're going to look at end behavior of a function, in this case just polynomials, and we're going to talk about focus more on using limit notation to describe that end behavior of the following polynomials. So, we have 4 here, and we'll talk about each one, and we're going to see how we can actually do this really quickly once we get good at it. So, A here, our polynomial is x to the 7th minus 3x to the 6th plus 45x to the 4th minus 321x plus 729. There's a lot going on here. But a polynomial is dominated by its leading term, which is its term associated with its highest exponent. This is a degree 7 polynomial. It's got an odd degree. Once I know that, I know both ends are going to go in opposite directions, just like with x cubed, or x to the 5th, or x to the 7th. This polynomial, I don't even worry about the rest. I know that it's going to behave like x to the 7th, and it's got a positive coefficient, so it's going to behave like positive x to the 7th. So when I'm thinking about what's going on graphically, I know that as x goes to positive infinity, the function is going to go to positive infinity, and as x goes to negative infinity, it's going to go to negative infinity. Remember, we're just concentrating on end behavior here. So let's talk about writing that up in limit notation. Let's take this end first. In this case, x is going towards positive infinity. So the way we write that up is limit, or LIM, as x, which is our input variable, goes to infinity. So this is saying as our inputs go to positive infinity, what happens with our outputs of f of x? They go towards also positive infinity. They go up. So that's how we would write it. For this one, we'd start off the same way, limit. Now x is going to negative infinity. X goes to negative infinity. Our polynomial, again, its name is f of x. This time, notice it goes down, so it equals negative infinity. So, a couple things to point out here. First off, when we have an odd degree, the ends go in opposite directions. Positive infinity, negative infinity. Because the lead coefficient was positive, going to positive x goes to positive y, going to negative x, going to negative y. So, again, we're going to try and generalize this so we can do this much more quickly. So let's go to B. We need to identify the lead term. Now you may think it's x squared because it's out front, but that's not the highest exponent. We look in here, it's actually out of order. Here's our one with the highest exponent. And notice I kind of take the sign with it. So this is going to behave like x to the 7th. Well, we already know how x to the 7th behaves, except this one has a negative in front. Remember that a negative in front gives us that reflection over the x-axis. So this one, as x goes to positive infinity, the y's are actually going to go to negative infinity. And as x goes to negative infinity, the y's are going to go to positive infinity. So it's going to be the exact opposite of what we had before. And let's look at why. Odd degree, the ends go in opposite directions. Negative out front, they go opposite. So when we're writing this up in limit notation, we have the limit as x goes to infinity of g of x this time. And when x goes to positive infinity, the y's are going to negative infinity. So that's equal to negative infinity. And for the other end, we have the limit as x goes to negative infinity of g of x. Now as we go to negative infinity, it's going up, so it's equal to positive infinity. All polynomials have 2 ends, so there should be a limit for both of them. And with polynomials, they're either going to go to positive or negative infinity. There's not that many possibilities. Alright, let's look at C. Now in looking at C, this thing looks like, oh my gosh, we have to multiply it out and it's going to be ugly. We don't need to multiply it out. We only care about the end behavior. So for large x, this thing is going to act like its leading term. So let's just multiply the leading terms together. Watch this. 4x squared is 16x squared. So we have 16x squared times 4x. So 16x squared from here times 4x from here, because that's going to be the biggest we get there, times 3x from here, times x from here, and times an x from here. All that's getting multiplied together to give us about what our lead term is. So we got 64, 172 for a coefficient, and it's positive. Remember, that's very important. And we got x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. We actually don't even really care what this number is. We just care if it's positive or negative, and based on our calculations, it'll be positive. Now, this is the first one we've had with an even degree. If the degree is even, both ends go the same direction. Because this is positive, they both have to go up to positive infinity, because if I put in 1,000, it's going to be a huge positive number. If I put negative 1,000, it's going to be a huge positive number. So both ends, as x goes to positive infinity, y's will go to positive infinity. As x goes to negative infinity, y's will also still go to positive infinity. So in even degree, they automatically have to go the same direction. So as the limit as x goes to infinity of h of x equals infinity. And all these pieces are necessary. Limit as x goes to infinity. Okay, well, as x gets really big, what are we looking at? H of x. So this tells us what the y values are, how they're defined, and this tells us where they're heading. Similarly, we have limit as x goes to negative infinity of h of x. Remember, we said even if we go to negative infinity, the y still go to positive. So it's positive infinity. They have the exact same, they go the same direction. The limits have the same answer. Last one, k. What we just saw is we don't need to multiply the whole thing out. We just need to look at the lead contributions. So x squared, 2x. This will be x squared. We'll raise it to whatever exponent. We don't need to FOIL it out. X squared. And a negative 2. So multiplying that all together, we'll have a negative 4. So that negative, as we've come to see, is very important. X squared, x cubed, x to the fifth. So, again, let's see what we got. Odd degree, negative coefficient. D is going to have the same answer as B, because we have an odd degree. They go in opposite directions. And with the negative out front, it's reflected over the x-axis. So as x goes to positive infinity, y will go to negative infinity. As x goes to negative infinity, y will go to positive infinity. And we already know now how to write this up. The limit as x, let's move that up just a bit there, goes to positive infinity of k of x is, as we see from our little diagram here, is negative infinity. Limit as x goes to negative infinity of k of x is positive infinity. So we have now found a shortcut for doing this without having to multiply everything out. All we do is we look at the lead term. If the lead term is even, both ends go the same direction. They're both up if it's positive, down if it's negative. If the lead term is an odd exponent, the ends have to go in separate opposite directions. If the lead coefficient is positive, like we had up here, going to positive gives you positive. Going to negative gives you negative. If it's a negative coefficient, it's the opposite of that. So that's how we can write this end behavior up in limit notation.